Bismillahirrahmanirrahim. Today, in lecture number 15 of Mechanism of Shear 2, we will have some new topics to discuss and find out different things. And these are about beams and shafts. So, title is the deflection and slope of beams and shafts, and finding this by double integration method or Macaulay's method. The deflection of beams and shafts. The deflection of a beam or shaft must often be limited in order to provide stability. So it is important finding this stability, providing the stability of beam, and for beams to prevent the cracking of any attached brittle material such as concrete or plaster. So if some brittle material is attached to the beam, so these deflection are important, and we have to limit it so that brittle material cannot destroy. Most importantly, though, slopes and displacements must be determined in order to find the reaction if the beam is statically indeterminate. For statically indeterminate beam, mean by indeterminate we cannot determine. Statically, by applying the method of statistics, and that was equilibrium equations. So by statically indeterminate means we cannot find the reaction by applying the equilibrium conditions. And that's why it is called as statically indeterminate. In this chapter, we will find these slopes and displacement caused by the effects of bending. So due to bending, we are discussing. Important definition for understandings include inflection point, where the curve changes from concave up like this to concave down. So that is where the curve changes. So at that point is called as inflection point. Only condition at a boundary. So condition at a boundary of beam. Let's suppose if there is a beam. So at left side, let's say x is equal to 0. What is the condition? At right side, x is equal to L. At full length, what is the condition? If it is fixed, then obviously there will be some things. We will discuss it later, but these are made of beams x is equal to L by 2. These will be with respect to space, means dimensions x, that is obviously covering the length in this case of beam. Continuity conditions, as name continuity shows, it's about something that is continuous, for the body to be continuous. So when different sections are taken, then the common point of both of the sections. So actually this sentence having the context of a beam. So in a beam, if different loading are being acted, so we will have to divide this beam into different sections. So we are discussing about those sections. So if different sections are taken, then the common point of both of the sections, left and right section, should give same value for deflection or slope at the common point of the beam to be physically continuous. So the elastic curve is physically continuous. So we have find out in each section the equations for slope or beam. So they should give same value. So that is at the common point. That is the key point in continuity conditions. So by applying both of these conditions, we can find the statically indeterminate beam, reaction of statically indeterminate beams. So statically indeterminate beams that there will be more unknown loading on the body than equations available for its solution. When a body has redundant supports, redundant mean extra supports, unnecessary supports, mean more supports than are necessary to hold it in equilibrium, it becomes statically indeterminate. So this beam is called as tie. Horizontal and tensile loading tie. If vertical compressive loading, this is called as column, and it will cause the buckling. Same here. And if horizontal but compressive loading, it is called as strut. And if horizontal but torque is being acted, then it will called as shaft. When axial compressive force applied on a vertical member, it is called column, like this. Beam is one which we apply perpendicular loading or transfer load. So this will not called be as column, rather beam will be like this, where transverse loading are applied. No load, just a simple bar. If load is not applied, we will say as bar, but when load is applied, then it will be called as some beam, and in this case one end is fixed and other is free. It is called as cantilever beam. So statically determinate, because there are two unknowns. One is moment and another is force friction at this spot, and both can be determined by applying this strategy. But in this case, when cantilever beam is this cantilever beam is supported here by a roller support, it becomes statically indeterminate because roller support is redundant. It is called prop beam. So this beam is called as prop beam. When cantilever beam is supported by a roller support, it will be called as prop beam. Roller support roller supports used if we don't want deflection at this point. Fixed or constrained beam, both end are fixed. Load is applied. Types of supports: pin support. At pin support there will be no linear motion, so linear reaction or force action will be there. Fixed support, no linear, no rotation motion, so there will be force action as well as moment reaction. And roller, and there is no rotation, so we will have only one reaction, that is upward, and only this. Simply supported beam, if one end is hinged, other is roller supported, that will be called as simply supported. So this is called as continuous beam because supports one is redundant, it is statically indeterminate. So continuous beam, more than two supports are there, that will be called as continuous. And overhanging beam, in this, when load is beyond the support, P2. In this, in absence of P2, simply supported beam, but when P2 applied with P1, we have overhanging beam. It is statically terminate. Now coming to our double integration method. Why is deflection? So we here in figure B we have shown the deflected shape of the beam, and in this diagram y is downward positive, deflection downward positive, x is right way positive, and a is the origin. Y is measured down, positive downward because deflection is downward. So in figure now we are drawing figure 1, and that is having some center of curvature, so it will be much beyond, not very close to it, and this from center to this curve distance is radius r, and angle is represented d theta, and this distance is dx, and for very small theta it will be straight line, can be approximated as a straight line. Curvature, that is 1 over r according to definition from some mathematics book, Thomas Finney, or you can consult some other books. So curvature 1 over r is equal to d square y over dx square over 1 plus dy over dx whole square and whole power 3 by 2. Since this deflection is very small, so its square can be neglected, so remaining is just this one, 1 over r is equal to d square over dx square. This is equation I. From figure 1, this figure, dx is equal to r d theta by L is equal to r theta. We have relation that 1 over r from here 1 over r will be equal to d theta over dx, and theta we know is equal to dy over dx. So remember, theta is dy over dx. So when you put here, it will be 1 over r is equal to d square y over dx. So from here and from here we have same then. Anyhow, we also know the bending equation, that is sigma over c is equal to m over I is equal to e over r. Remember, in this equation y is upward positive, but here we are driving y downward as positive. So to compensate that, I have written here minus. So 1 over r will be equal to minus m over ei. When you compare this equation with this equation, 1 over r is equal to d square y over dx. So result will be d square y over dx is equal to minus m over ei. Can be written in this form: m is equal to minus ei into d square y over dx square, where y is deflection and x is length of the beam from origin. So this is equation 1 in red, written in red. The first integration of equation 1 gives slope theta of the beam at a distance x along its length when the origin is taken at point A. So theta is equal to dy over dx. So what we are having the integral of this. So integrating this with respect to x will give us minus m over I dx plus c1, and c1 is constant of integration. The second integration gives the deflection y of the beam, and at which point that will be determined by putting the value of x. So if x is equal to 0, then it will be point A. So y is equal to, again, integration of this equation will give us double integration minus m over ei into dx plus c1x plus c2. c1x first constant of integration, c2 second constant of integration, where c1 and c2 are constant of integration, which can be evaluated by the unknown condition of slope and deflection at certain point, usually at this port. So now at the moment these are unknown. To find these, we will apply boundary condition as well as continuity equations if necessary. So here we are just applying the boundary condition. For simply supported beam, y is equal to 0, m is equal to 0. For simple support, this is y 0, m 0. There will be no moment, no deflection, no moment, bending moment, but slope exists. For fixed support, deflection will be 0, slope will be 0, but bending moment will exist. So these are for some sports. So here these are generally found out. To integrate one, we need to find m in terms of x. So this m, if it is in terms of x, we have to find out m in terms of x. So for that, if this is the case of simply beam shown here, ABL, and load is acted at the midpoint